Hello guys, welcome to a new lecture of doubly reinforced rectangular section using the limit state method. So as we have discussed the type 1 problem, so this is a type 2 problem in which we'll have to find out the area of steel in compression as well as tension. In such type of questions we have basically different values given in the question, which are as follows. The dimension of the section of the beam is given, that is B and D. Also, with this given data, there are grade of concrete and grade of steel is also given. So, we'll start the numerical by using different steps, which are as follows. The very first step is to calculate XU max value, or this is also known as XU limiting value, and this totally depends upon the grade of steel. For different steel, section 250, 415, 500, we have different values like 255.53.48 D. D is the effective depth 4.6 D. So this is the different value for the XU max, which we'll calculate using the effective depth. So the second step is we'll assume that the section is balanced. The section is balanced section, and as the cross section of the beam goes like this, there is the neutral axis, that is XU, or is equal to XU max. Here we have 3 reinforcement. Suppose we have 3 reinforcement here, so it will goes like this. And if we draw the strain diagram for same section, which will go like this, as we have discussed already in the previous lecture also. This is the neutral axis, this is the zero line, and suppose this is the maximum strain in the tension zone, that is epsilon st is equal to 0.002 plus what is 0.87 fy upon es, and this is the maximum strain in the compression zone, that is 0.0035. Now for the steel in compression zone, there is a value called epsilon se. Now in order to calculate this value, we'll use the similar triangle condition, and different values which are known will obtain this formula, which is ESC is equal to 0.0035 into XU minus D dash is nothing but the effective cover from the top compression fiber, and XU is as we have calculated XU max, and XU is equal to XU max, so we'll put the value here, and we'll obtain some strain value, and there is a chart in which for every strain value there is a stress value given. If the stress value resembles that the strain value resembles that chart, then we can directly calculate this FEC value, that is stress in the steel in compression. But if it is not given, then we'll consider two values of strain and stress in steel in compression, and suppose A and B are the two values that are known for that are known in the table, that has values x and y. Now there comes a value A dash or B dash, which is in between A and B value, and that has some unknown stress value x1. So if this value is unknown, we'll use interpolation formula that I have already discussed in the video, and from that video you can get an idea how to calculate that value. Now after calculating this stress in steel in compression value, that is FSC, we'll move towards the fourth step, in which we'll find out MU limiting value. From this value we'll get to know whether the section is singly reinforced, or whether the section is doubly reinforced. Now there are two conditions. After calculating this MU limiting value by this formula, that is 0.36 FCK B into XU max D minus 0.42 XU max, Now after calculating this value, we'll get to know two conditions. That is, if mu limiting, that is the bending moment. Mu is nothing but the moment of resistance. Moment of resistance is nothing but the maximum bending moment that a section of the beam can resist. Now this maximum bending moment value is less than, if maximum bending moment value that a section can resist is less than this mu limiting value, then we can say that the section is singly reinforced. Now for that singly reinforced, we'll directly calculate this AST value that is given in this formula. Now if the second condition is, if this mu value, that is MOR, ultimate moment resistance value, is greater than mu limiting value, MOR or maximum bending moment of any section is greater than mu limiting value, then we'll calculate this doubly reinforced, and that then we'll get to know that the section is doubly reinforced. Now for that doubly reinforced section, we'll have to calculate area of steel in tension and area of steel in compression. Now for that we have to calculate one ultimate moment of resistance, that is a new value for doubly reinforced section, through which we'll calculate this area of steel in compression. Now in order to calculate this ultimate moment of resistance for the compression zone, we'll simply do what that we'll subtract maximum bending moment, or the moment of resistance, ultimate moment of resistance value with the mu limiting value. Now using this, we'll find out this value that we'll use in the calculation of area of steel in compression. Now the fifth step is to find out AST. AST is nothing but the area of steel in tension, and area of steel in tension has two values, that AST1 and plus AST2. Now in order to find out this AST1 value, that is the area of steel in tension zone, we'll use mu limiting value in one formula, and that is AST1 is equal to mu limiting upon 0.87 F by bracket D minus 0.42 XU max. That is the old formula, and the second formula is AST2. In order to calculate this area of steel in tension, the second area of steel in tension, we'll simply use this value, mu limiting value. Now that mu2 limiting value, that is mu2 upon 0.87 F by into D minus D dash, and which will calculate us the value of AST2, and on combining these two values, AST1 and AST2, will calculate AST, the total area of steel in tension. Now the very last step and the sixth step is, in order to find out the area of steel in compression, just the compression zone. Here are two zones, that is one is compression zone, another is tension zone, and there is a neutral axis in between both. And in order to find out the area of steel in compression zone, we'll use the second ultimate moment of resistance that we have calculated by using by subtracting both the maximum bending moment minus the mu limiting value, and the formula goes like ASC is equals to mu2 upon FSC. FSC is the stress in steel in compression that we have calculated in the same question in the previous steps, and D minus D dash. D minus D dash is nothing, D is the effective depth and D dash is the effective cover from the top of the compression fiber to the center of the reinforcement in the compression zone. So by using all these formula, we will calculate the ASC, and in the previous step we have calculated the AST. Now by calculating both these, we'll find out the area of steel in tension as well as area of steel in compression. So that was a question all about. We wanted to find out the area of steel in tension and area of steel in compression. So thanks for watching video.